well. This is our going to be our new office. So, um, where we bought this building a couple of years ago, and it just kind of sat there. And I spent my weekends going out there and demoing things. So, anyways, this is sort of what we put together really quick. Our firm is really based on really low carbon. We do a ton of residential work, especially with COVID. Usually we're kind of 50-50 commercial to residential, but right now we've been doing a ton of residential, as you can imagine, with what's been going on. So we really focus on low carbon, low embodied carbon, as well as operational carbon, which the operational carbon is your energy use, and the embodied carbon is the amount of energy that goes into the materials that we use to get you that high operational energy. And so in some instances, the embodied carbon that goes into an insulating material, for instance, may not pay off on the operational carbon side of things because of how we get our energy here in the Northwest, and just because of how carbon intensive it is. So spray foam is a great example of that. Like, you'll almost never get the payback from spray foam, even though you're gonna have lower utility rates or utility bills. You're gonna have a really airtight, really well insulated building, but it's such a carbon intensive and climate, global warming impact from the blowing agents. It's so bad that the payoff is not worth it. It's actually better for the world to have a little bit higher utility, it's not much, but utility bill, and use a more inert insulation such as cellulose, or even fiberglass bats, are now no longer have all those nasty chemicals in them like they used to. So those are the types of conversations we have with folks about those materials. And then all the materials that unwittingly tons of conventional materials have nasty glues and VOCs, and spray foam is another great example of, like, when they install spray foam in a home, you can't be in the structure. Nobody can be in the structure for a week while it off gases. Well, I don't know about you, but I don't think I ever want to live in a home where the material that went into it, I don't care how far in the wall it is, somehow was already off gassed in a week. And somehow, while I'm going to air seal my house really well, and this thing is done off gassing, I don't trust that. And I think there's better ways to get to find that solution without using that material. So we try not to use foam as much as possible. It's not to say that there isn't times where we have to, but there are different foams, and some foams are less bad than others. Polyisobutene is a great, much lower carbon impact. They all have fire retardants in them, unfortunately, but that one is, when we have to use it, it has its place. And there's alternatives to, XPS. Now there's GPS, there's EPS. All those products are much better than the blue and pink foam that you buy at Home Depot. That stuff is awful for the world. So spray foams and XPSs are bad news. So if you have to use foams, if you're like forced to use it, there are other products out there that are better, and are becoming more readily available as well. So you can get polyisobutene from Home Depot. Sometimes you have to order it, but you can get it within days. So that's kind of what we focus on. But we also talk about sustainability. So there's the environmental sustainability, but we also talk about social sustainability. So this project here is a great example of, these are 3 fee simple lots that share the interior. So house ADU, house ADU, house ADU, and they share the lot in the middle. So, you can have all your solar panels, you can have all your high tech stuff, but when the shit goes down, you're going to be all alone in your house, right? So if you don't have a group, a clan that you can sort of work with and sort of share, all the power went out, and John over there's got a generator, let's all plug in, something, that social sustainability is really important, I think, as climate change starts to become more of an issue. We have more emergencies, and we have more storms, and we have more of these issues. So I think that's important to think about too. And that has to go with how you design a space around having semi-public space, having public space where people are outside, people are encouraged. The way we design these is they all have garages off the back. There's an alley here, and they all have garages. None of them have doors that go directly into the space. So you have to go out of the garage, walk around, and walk in your front door. Now that's kind of a hassle. It would be more convenient to be able to walk right in, but it encourages you now to walk through that courtyard, and now you might have an opportunity to have an encounter with your neighbor, to say hello, to talk about something, to whatever that is. So instead of being able to drive in your garage, close the door, nobody sees you, next day you go to work, when we go to work. So those things are important, and we design things intentionally. We locate the trash stuff in a place where someone will have to walk across to have that encounter. So it's sort of sacrifice convenience for that social impact. And like all these houses have front porches, right? So you can post up out here, see your neighbors, talk to your neighbors. They all have porches in the back, so they all kind of look onto that space. That is equally as important in our mission to the sustainability piece. But this project is almost all techno nerdy energy details, but that is also something that we talk a lot about in our work, especially on the residential side. So basically, this is sort of how we've organized the presentation, talking about how we destroyed the place, then built it back, and how we air sealed and insulated things. And then, the building's not finished, so there won't be finished pictures. But there'll be lots of nerdy construction photographs as we go through. So the building was originally built in 1940 as a dentist's office. The dentist had it built for himself, and quickly did an addition. It's hard to tell exactly when, but this little bit on the side was added on, like almost immediately. It seems like they almost like maybe drew the plan and then said, "Oh, wait, we forgot a room," and added it on or something. But over the years, it's been a lot. So it was a dentist's office for 40 plus years. And then I think the dentist's son, from the records I found, turned it into a pizza joint, Montevilla quality pizza, which gives you the hint that it's really good quality. And then it was a coffee shop, a cafe, a barbecue pit, a tattoo parlor, medical marijuana shop, growler filling station. It was all these little things, but never for a long time. But the building really kind of fell into disrepair. And it is a unique, as you can see, it's kind of unique for Portland. It's also, very unique for Montevilla to have a kind of this Art Deco style building. So I live in this neighborhood. I used to see it all the time. It was always a curious building to me. And then when it was for sale, I thought, wow, this could be our new home. Little did I know what I was getting into. So the building was in quite disrepair. It hadn't been maintained very well. There was water damage in the ceiling. You can see in this bottom edge here, there was a lot of rot and termite damage that we actually had to remove. That actually had just rotted away. Someone had taken it apart. This rim joist here, it was in pretty bad shape. The wall was built, it was originally built, you see this white up here at the top. This is 1/4-inch plywood, and that was the original skin to the entire building in 1940. From what I can tell, it was just this white 1/4-inch plywood that went around the whole thing. And then at some point they added the stucco from the red down. It stuccoed it from the bottom 10 feet, and the top 2 feet remained plywood. And then they added more layers of plywood over the years as the plywood sort of degraded. They just added more layers. So there ended up being 3 layers of plywood at the top that, as I started to take it apart, I realized that there was just rotten layers on top of rotten layers. So as we started to get into it, we were like, oh man, this is more than we had thought we were going to do. So we just move our little office in here. But a lot of the windows were boarded up, broken, missing. This is the north facade, and it didn't have stucco. It was just plywood that was painted, which has been removed there. There was a lot of habitat living in the ceiling. You can see one of the rat's nests here at the bottom. There were 4 rats' nests and 2 squirrels' nests. Some were alive, some were not. Finishes were just worn out. It had sort of like lived its life, but it did have these kind of cool ceiling details in here. You can see these cove details that I went to great lengths to try and save in most rooms as much as we could. But you can kind of see as we started to take the roof apart that it was in rough shape, some of it. So this was the floor plan. It had a load-bearing line right here, and the way it's framed, as you can kind of see from this, you can kind of see it here. There's these joists that are running this way. That is the ceiling joists, and then above that were 2 by 2x4 ceiling joists that went along from here to here, and then it had ceiling joists at 2x6 right here. You can see we have our little rat resident in here at this existing assembly. And so the building was completely uninsulated. So you had 2x4 walls, you had 2x4 roof, you had 2x10 floor, and there was no insulation. It had plaster finishes everywhere. So we started thinking about, okay, how are we going to get this floor plan to work? Some of the challenges were the bathroom and all the sort of kitchen area stuff was like right in the middle, and the plan doesn't sort of lend itself to sort of blowing it wide open. Also, some challenges of having to make an ADA bathroom possibly through the city would eat up, quite a bit of square footage in the building. So we sort of had to navigate that as well. But a door here, lots of doors, lots of circulation paths. And so, we had some challenges here on how to get it to work without trying not to like create a huge structural implication impact. Then the other challenges were, how do we insulate this? If we want to do a really high performance project, and that was our goal, was to do a really high performance project, but to try to do really low toxic materials, and foam insulation is really highly toxic, off-gassing, has filled with fire retardants, all of these things that who knows what they're doing to us. They say that they don't, but they. So one of the things about this assembly is that because we don't have a lot of room, it's saying basically to insulate this, we would have to use foam. On a flat roof, a lot of times it ends up being foam. And so we were like, okay, we're kind of stuck with having to do foam here. Okay, we'll just have to bite the bullet. So in this case, the best solution would have been to put the foam on top of the ceiling, but then we would have to raise up this parapet so that the water detail would work. And so then we thought, okay, we're gonna have to raise this up. So if we do that, maybe we should start looking at, well, if we raise it up, let's change the ceiling assembly so that we can maybe get away from using foam possibly. And then how do we do the walls, insulate the walls with the existing 2x4, but also add some more insulation to sort of over insulate a little bit. We're not going to get to the passive house levels, but we're going to be able to get a little bit more. And part of the challenge is, every inch in here counts because it's only 578 square feet. So it's not a very big space. And, you start to build in walls and you're sort of stuck. And you're also limited to the stucco on the outside. You can't really go out because you've got stucco. So we were sort of really kind of walking this narrow line of how we could do this renovation without using foam, spray foams, things like that. So we started taking it apart. You can see up here, there's that last layer of plywood. You can see the rot. It's all bubbled and buckled and not looking so good. And this is the floor plan we came up with. So we moved the load bearing line over here. So because the move sort of kept the spans the same, we didn't have to do any real structural work there. So this will be our work studio, reception, entry area. We moved this door over to where there was a window here, so no structural impact there. And so it's a little more efficient through a little kitchenette, the bathroom, conference room, and then a little front office there. And then we put an ADA ramp going up around the back in order to avoid having to upgrade the bathroom. Was as an offset, we'll get people into the building, and then we can save room on the layout. So here's the section through the roof. Now that we took those 2x4s off and we came in and put TJIs, so engineered 14-inch roof joists that span the entire length. So instead of having to have these cut spans, 2x4s don't span very far, the TGIs were able to span the whole thing. So this is the existing top plate that before the roof was down here, we set the TGIs on top and made the roof now 2 feet taller. So the building gets 2 feet taller. And what that allows us to do is now fill this with cellulose insulation, 15 inches of cellulose insulation. So we get like an R50 something with that. This is a kind of an edgy detail, because in a flat roof, you're really not supposed to be using cellulose because they don't believe that there's enough airflow. Because moisture can get in here. But the way we designed it is the air comes in here, there's an air gap here, a really low one, and then we create kind of kind of what I'm calling a mini attic, where this airspace then can build up heat, and it starts to draw the heat, and then it spills out the top through our parapet. We've got this little detail where it vents here. So, and then to sort of put belt suspenders on that, along the top, on the bottom of the or at the top of the service cavity, we put in a really smart vapor barrier, which then keeps any moisture from the inside of getting up into that assembly. So if we keep the moisture out of the assembly from people and people creating moisture inside the space, then that it's going to make sure that there's no mold up in here, right? So by doing a really tight envelope, we can solve that. And then we added insulation to the outside on the north wall since we don't have plaster, and then we added insulation to the inside since we have plaster on all the other walls. And so you'll see that as we start to take it apart. Here's the finished room. We start to disassemble things. We saved this roof cavity and started to pull the plaster down. We saved a bunch of this lath, thinking like there's going to be some value there. Maybe we hadn't really had an idea of what to do there yet. But you can see sort of the state of the floor. It's basically Swiss cheese everywhere. The roof is off here, so light's coming in. And then here's where we've reassembled things, and we started to put the insulation back in. So we've got dense pack insulation here. So you'll start to see that as we go through these. Some of the unique details are this roof assembly as we sort of saved some of these. And then at the corners where you've got these rounded corners, they didn't have a bottom plate. You just have joists coming down and kind of making that radius. So there were some unique details that, you know, from an air sealing detail, hey, how are we going to keep air from getting through these cracks? It's really difficult in these locations because of, you know, it's not standard construction, because the curve, it's just a weird thing the way they built it back then. So you can start to see the layers coming off the top here as we start to take it apart. Now we've got it down to the studs, and you can see there's all kinds of stuff going on here that we needed. You know, there's still the chimney is shown here, which we ended up removing. In the back, they had started to build a deck because this was a coffee shop sort of thing, and they had a door so people could come out and sit on the deck. And this is all PT lumber, which again, you know, is toxic to a certain degree. And I didn't want to, and it was in fairly good shape. I didn't feel like I wanted to throw it away. So we saved it, and I didn't really know what we'd do with it, but I was like, hey, well, let's save this and see if there's some use for it. So just trying to, the other thing I would say is that when we were taking this apart, I was salvaging the 2x4s and the 2x6s that we were taking out. So one of the things that's a challenge when you want to salvage lumber is the amount of labor that goes into removing nails and getting it ready. So it actually is cheaper. Well, that might not be true today because of lumber prices, but typically it's cheaper to buy new lumber than it is to salvage old lumber because of the work that it takes to get it back to ready to be installed, mainly taking the nails out of it. So I was out there on the weekends taking nails out myself as sort of, hey, I really want this to happen, so I'm going to just do that myself and have it stacked up and ready for the framers when they show up. And feel free, anybody on here, if you want to ask questions, anything pops up, please speak up. We don't have a big group, so no harm if you want to ask some questions. So let's see. This is sort of as it's coming apart. You can see the ceiling assembly here. The 2x4s are sailing over the top, and then the 2x6s are down below for the ceiling, and then the roof framing here. So this is before we've taken the roof off. One of the things that they did is that as the 2x6s are coming across, and you can see that in this section, sort of, it's not drawn exactly right, but these 2x6s are running across. This 2x4 comes down, and it is actually lower than this. It notches. These last 5 2x6s get notched. So they're actually, when we look at that, you'll see these huge notches that they put in. These are, and you could see the boards bending. It was really not a good assembly. So we ended up removing these 2x6s and replacing them. So here you see the building getting taller. You can kind of see the TGIs, the framed roof joists up here, spanning the whole thing. And we built up the parapet. You can start to see some of the salvaged wood showing up in here. Some of it's new, some of it's salvaged. mixed in. So it reduced our lumber package. So we reduced our footprint there. Our lumber package is fully FSC from Sustainable Northwest Lumber. We did everything FSC as much as we could. So you can see that the parapet gets taller, the building starts to get taller, and then this stuff, as we started to go around, we realized this is just rotten. So we just took it off and started putting new plywood up above the plaster. Here's where we replaced those ceiling joists in here, in the back of the structure. This is where the low end. And then again, you can see in here, back to that section, now we're able to get, the gray is the insulation. So now we're able to get this 15 inches of insulation plus our service cavity. So the nice thing about a service cavity is that our air barrier is above the 2x6. So no moisture can get past that. And all of the things that normally, so in a normal house, like a conventional home, the air barrier is your sheetrock layer that's painted. That stops moisture from going through. Well, when you have a light up there sticking through, now moisture can kind of make its way through that, and it gets up into that ceiling, and air and moisture and your energy, your heat goes up through there, and vice versa. Heat, when you're trying to keep cool, comes in. So all your electrical boxes, all your lighting, all of that penetrates that barrier. So what the service cavity does is it allows us to put all of our electrical, all of our lighting down in this 2x6 plenum with a nice clean vapor barrier across the top, no penetrations, so that it's we can run what we want. We don't have to be very careful about sealing all those little penetrations. So that can be really beneficial to hide your vapor barrier deeper into the ceiling and also into the wall, if you can pull that off. On the walls, we basically put the vapor barrier at the back of the sheathing, again, to keep all of our electrical inboard of that. And the way we achieve that was through the Aero barrier system, which I'll talk about in a second, which is a really neat, really cool system, which I highly recommend for retrofits. And then on the floor, you have, we basically put new plywood down on top of the Swiss cheese floor that was there, and taped all those seams. So we get a nice, you can see we get a nice, this red line is a nice tight air barrier around the envelope. So that keeps air from infiltrating out, which then now we know that'll keep us, no matter how much insulation we have, if air is leaking out, it doesn't matter how much insulation you have in the wall. Well, it does, but this is going to do a better job of keeping your heat in. So the challenge with this is that the assembly becomes really challenging, right? Because we're putting roof joists on top, and somehow I need to get this vapor barrier on here while the framers are up there putting the new roof joists on. So you've got this vapor barrier here you can see the tape lines, and they're putting the joists over it, and these guys are walking on the vapor barrier, right? So it's not great. I'm running around, they're dropping nails. They're also not, these framers are not super knowledgeable about tight energy retrofits. So they're dropping nails on this thing. They're just not being, I'm trying to I'm out there sort of babysitting them, running around taping seams that they're breaking. And yeah, it was kind of a nightmare. So, but anyways, going around and sealing this against the edge of the wall, taping it, and we reduced all of our roof penetrations to one penetration for the stack vent, which everything went to one spot, and then we popped it up and we sealed that through the vapor barrier system. And you can see that the pipe, of course, comes up right where there's a TGI. So we had to do a little jig jog to get around it. So that was, some of those challenges of like, and this is, I think, a challenge with any retrofits where you're trying to do a deep energy retrofit, is that most builders are not familiar with a lot of the things that I've been talking about here. So when they come in, you have to do things differently. You have to talk to everybody differently. And I learned a lot on this, and a lot of mistakes happened, which I'll go through, where I wasn't in front of that because I didn't anticipate there would be a problem. And the communication, I just did not communicate it well, and people did some things that I had to redo. So you can see you can see that vapor barrier here over the service cavity. Now we're running our lights, we're running all of our electrical down in here, and this is staying pure up above, and nothing's penetrating it except for that one pipe. And then you can see it over in this room as well. We taped all the floor seams, so that now that stops vapor from going, or stops air leakage from going through the floor. because the plywood will act as that barrier, and then the taping the seams and around all the edges. This is the transition from that the upper portion that we reframed, and the stucco. There was a gap there which we sealed with this flexible flashing tape. And then around these tough corners that I showed you earlier, you know, that was a real mother scratcher because the framing was all wonky and getting that sealed was tough. So there were some really tough bits in this. So this is the Aero barrier system. So once we had it stripped down to the studs, now there's all these little, you can see in the walls, there's all this skip sheathing, these gaps, and you know, those little corners. You know that there's air. There's no way to really do a great job of sealing this. So what Aero barrier does, it's a system where they come in and we tape up as much as we can, the stuff that we can see. They put in a blower door. They set up a blower door system where they blow air into the space and they pressurize the space. So this is usually they'll do this to test the air leakage of a structure. So that's blowing air in. It's creating a pressurized system. And so that means the air is trying to find a way out. And so it's finding those holes and it's zipping out. And then what they do is they have these little sprayers that are connected back to these buckets that are at the bottom of this picture here. And they're pumping this fluid, and it's almost like rubber cement in it, but it's non-toxic. And it goes into these sprayers and it sprays a mist into the air. And then the air goes and finds those holes, and this goo goes and finds those gaps and starts to accumulate and seal those holes. So you can see here this white sort of gooey, it's sticky material has found all these air gaps and sealed it up from the back of the sheathing. And so it seals up all these little gaps and all these little holes. So it's perfect for a retrofit where you're really trying to get a good air barrier. And we wanted to hide our air barrier in the wall, like I said. So if you put the air barrier right behind the sheetrock, someone could easily poke a hole through it. All your penetrations are coming through it. Here we've got the air barrier buried in the wall at the back of the sheathing. So this took all day to go down, to seal to a point where it was acceptable. So when we first started, this is the report from when we started. We started with 48, 1,200 CFM of air leakage, or 14.8 air changes per hour. That's leaky, really very leaky. And then afterwards, we had 48 CFM of leakage, 0.59 air changes per hour. So passive house is 0.6. So we got this leaky old building just below passive house standard for air leakage. So we were pretty excited about that, pretty pumped up. I didn't think we'd get that low. I thought maybe 1 ACH, but we got it down to 0.59. So I was really excited about that. I had heard stories from people saying like, well, the Aero barrier will get you down there, but that probably won't be, you'll probably lose some of that towards the finish line. I thought, oh, you know, what could go wrong? Which I will let you know what did go wrong as that went along. So now insulation comes in the roof. This was a real challenge because the way the assembly is set up, we've got our air barrier over the ceiling, and then we're putting the insulation on top, and then we're sheathing over the top. So I had to insulate from above. So this is a real coordination challenge because usually they insulate from below, but because we can't see the cavity because we have the vapor barrier in, it's kind of an order of operation that was a real challenge. We had to insulate from above. So the guys come in and insulate from above. So I had to have the inspector come, give me a partial inspection on the roof joists. Then insulators come, insulate, then framers come back, put down the plywood, and then get the roof on. And of course, right when we got the plywood back down, there's a storm coming. So we put a tarp over the whole thing. This storm, it was like early in this spring, we had this really hard rain, like over 2 inches of rain in a day or and a half or something. Well, of course the tarp leaked. So this was before the insulation went in. The tarp leaked. I show back up the next day, and there's pools of water sitting on the air barrier, like just dripping into the space. So I had to shop vac all that out. And then the insulators were coming later that day. Then we put the roof on, and again another rain came. Luckily, we put a second tarp on it. So now, the order of operation just was a challenge in some of these. So that's something that, you really have to, a lot of thinking, lots of coordination running around. And then of course the rain, which is always an issue. So in the service cavity, below all that cellulose, we put in, I found this product called hemp wool. Hemp wool is carbon positive, right? It's just hemp, which absorbs carbon while it's growing. So there is a little bit of, I think there's a little bit of polyester in this for fire rating, but it's like almost 100% hemp wool. This stuff is really cool. Like it smells like grass. So when you put it in, it's got this real natural feel. You can rub it on your face. You can lay in it. It's completely natural. It's, there's no other insulation except for maybe recycled denim that you can do that in. So it's completely healthy. It's not off-gassing. It friction fits up inside there, so it's really easy to install. Cutting it was a little more of a challenge. I think a table saw would have helped me a lot, but I had a grinder with a metal blade that was sort of working through it. But you can see nice install underneath the cavity here. The guys came in and did the dense pack cellulose, which is a standard situation. And then, they just come in and do that, which I'll talk about in a minute. And then we installed these Gutex panels. So the Gutex is a German product. 475 Materials sells it. Brad can put up links here if you guys are interested in the chat, if anybody's interested. It's carbon positive, or carbon negative. I get that backwards. It's carbon negative where, it's a wood fiber waste product that is put in with a resin in there that's non-toxic, and they come in different thicknesses. They're designed to go on the outside, just like a mineral wool board would go on the outside. But because we have the stucco on the outside, I put it on the inside. And that gives us a nice thermal break. So we get R14 in that dense pack, and then we get another R6 on the Gutex by just screwing that to the inside of this wall. And then the idea would be the wall board goes over that. So in this room, which is our conference room, we're actually going to have a big piece of glass right here that will act as a marker board, and you'll be able to see the Gutex behind it. So a little bit of a truth window, so people can come in and see what that looks like and see the product. We're also going to do a window in the ceiling so people can see the hemp wool. So sort of using the finishes, these really sort of alternative materials as finish, so people can see it and we can have conversations about it. A lot of these, as an aside, a lot of these alternative materials don't cost a lot more than standard materials. The challenge is they don't have distribution because they're still sort of getting off the ground. They don't have them in Home Depot, so you have to have it shipped to you, and that's where the cost gets crazy. So, it would be $600 to ship a pallet of this to me, and the product itself only costs $1,200. So it's like, half of it is, it's just like triples the not triples, but goes up by a third. And then, this stuff is also doesn't turn corners, and we have these round corners in this Art Deco building. So I found these hat channels that bend. Simpson makes these hat channels, and so sort of bending those around the inside corner. And then my plan is to fill this with a mineral wool board that will sort of just push it into that, and then the wall board will hold it in. So we get a nice thermal break there as well, and get those corners, and then the Gutex will come up and butt against the end of it here. So things to look out for that I learned, when we were talking about the air barrier in the ceiling, fighting the framers because that order of operation was so difficult. The insulators came to do to put in the cellulose, and early on I had talked to their salesperson, like, hey, yeah, I'm trying to not do any spray foam in the building. Oh yeah, cool, yeah, that's cool. And then spray foam, the cellulose guys show up. They start doing their thing, and I couldn't be there. So this is sort of like, I couldn't babysit them. I was babysitting everybody else, and it was taking up all my time, but I had to go to a meeting. I couldn't be there. So I thought, well, what could happen? They were just putting cellulose in there, but I hadn't thought about that they're also going to be putting spray foam in. So they just showed up, and their standard installation was anything smaller than so much, they're going to fill it with spray foam. So you can see this white line here. They just pack that with cellular or with spray foam, this with spray foam. So it was really heartbreaking that they ended up doing that, because I was really trying hard not to have any spray foam. So it was one of those things where, like, well, it's there now. What are we going to do? So the Gutex will go over that. So I would have rather just stuffed bats in those little gaps. Another thing that happened is they put these screeds up in order to do the dense pack. This is like a polyester mesh that they put up, and then they cut holes in there, and they spray the cellulose in there, sorry, and it packs into that mesh. That screed sort of holds it in there and allows them to get it really packed tight. So, but when they put those in, they put thousands of staples, down the studs. Well, at the bottom, what they did, and I realized this after the fact, is that they cut their screeds with razor blades, and you can see what it did. It cut this huge gash in the tape that I had spent all these hours sort of taping everything meticulously and doing all this. Put the air barrier in, like we had talked about, and this is where they were saying, oh well, that's your 0.59 is what you got for your ACH now, but that's not what you're going to end with, and these are the reasons why, and so I was like, I can't believe this happened. So I have to go around and I had to reseal all these gaps around the edge. And it's, again, comes back to conventional construction does not, it's a different mentality of how you do things when you're trying to do a high performance. You have to have meetings with the crew. You can't just tell the boss, because the boss doesn't always send it down. You have to, all right, everybody gather around, take all your razor blades and go put them in the truck. We don't have any. If you want to do, you have to check out razor blades over here at the library or something. You have to figure out a way to I don't know, to control that situation. Yeah, that was tough. We did outsolation, so mineral wool on the north wall. Since we didn't have stucco, I thought, well, let's try a different system just to, again, create an example. So what we did was, we've got our building paper. You can kind of see a window of that here on the wall. We zipped the rock wool panels, which mineral wool panels are 1.5 inches. We use these roofing washers to sort of tack it in, and then we put cedar vertical battens in their 3/4 inch, 1x2s on the wall. And so you put those on and you use screws to kind of plumb them up. And at the bottom, we put this little J metal. You can see a profile of it here that I had made with the depth I wanted. And what that does is it allowed me to set the rock wool, the mineral wool, down on that, and set the furring strip down on that. And then I'll put my siding over this, and this will act as a bug screen. And so it was really kind of made the install really slick, because you could set your rock wool down on that and just kind of stack it up. And then everything lines up, and then you put your siding in and you've got a nice sealed thing. So instead of trying to do that with a mesh or something, this seemed really slick. And it wasn't that expensive. So that was cool. Up here, also I should mention, we had those, now that we have these new TGIs now, we were able to sort of have that sail out a little bit further out over the back, so to get a little more rain protection back there as you're walking in and out. And we used that old lath that I had taken off the wall, and we used that to finish the soffit up there, and we used it in a couple other locations. So kind of reusing some of that material where we know it's not going to get hammered with weather, since it's Doug fir and it's not great in the weather. You can also see the mini split system, which is already set up here, which we can talk about as we go on. So then the siding starts to go up, and this is basically juniper, came from Sustainable Northwest. It's landscape grade juniper, so it's true 1x6 rough sawn. And when they say rough sawn on this material, they mean it. It is really rough. Like it would be like 1.25 inches down to 3/4 on some of these boards, and from 5 inches to over 6 inches, 6.5 inches on other boards. So I thought, well, I'm saving all this money. I'm going to put this really rustic wood up there, and it really, the labor in trying to get it to line up was probably worth buying the kiln drying version, the stuff instead. But one of the things when we put this up was juniper, a lot of, the challenges with wood in the Northwest is that it needs to be stained, needs to be refinished every few years, depending on its exposure. So this is north facing. I was less worried about UV exposure. It's under a big overhang. I was not so worried about rain beating it up. But also, once you stain something, you're sort of having to keep restaining it if you want to keep that warmer look. So we decided to let it gray out, and the benefit of that is we just let it gray out. When or if it gets rotten or needs to be replaced, it's because it's on a rain screen, we can take the board off, put a new board on, and not have to worry about how that affects the wall so much. The other benefit of not staining, not finish, not sealing, not staining, is that when the wood is at the end of its life, which it will, no matter what you do to it at some point, you can compost it. It doesn't have this chemical in it now that you have to throw it in a dumpster, take it to a landfill. Now it's just its natural state. You can make firewood out of it. You can, put it in your compost, whatever you do. So that was our driver there, is to try to not seal and paint as much as we could, knowing that, over time we're going to have to replace these boards. They won't maybe last as long. If they last 15 years, then we have to replace them. But knowing that the carbon impact of that and the landfill impact of that is worth the having to sort of keep up on it a little bit more. Some of the details here, I don't know if you can see here, but you can see in some of these other areas, reusing all that PT that was already out there that someone was building a deck with. We designed over here, we designed the ADA ramp out of wood, and we reused all that. We designed it so that the spans would fit a 2x6, because that's what we had. So that the spans are short. We made sure that this thing stayed less than 12 inches off the ground, which then allowed us, and the slope was less than 1 in 20. So that allows us to minimize, we don't have to have a railing, we don't have to have a curb, and it's just open and simple, easy. It's just it doesn't even have to be permitted. So it can just sit on blocks that you buy at Home Depot. You don't have to put in this massive footing. So that was one of the, no concrete, reducing the concrete impact as well, which is also a massive carbon hitter. And then reusing all this PT, which would have just ended up in a dumpster somewhere, or I guess I could have put it out front and somebody would pick it up. But, we try to reuse that as much as we could throughout, ripping out those PT pieces to reuse it.
And then we had a quick question on how the internal walls were insulated.
Yeah, it was dense pack cellulose with this screed they put over, and they put that dense pack in there, and then that was the first layer, and then we're coming over that with a Gutex wall board, which is a wood fiber board, which is R6. This is a German product, and that we just screw to that, gives us a nice thermal break, gives us a nice blanket of insulation on the inside, and then we'll put our wall board right over that. So hopefully that answers that. And then the floor, we did just dense pack. We did like a high density fiberglass insulation underneath in the floor. There's not a lot of options for down there if you're going to be open underneath it. At the top, now that we've made this thing taller, we battled over how do we finish this top. We talked a lot about maybe we come in with metal. I mean, the idea of like how do we uplift this Art Deco building and make it pop a little more? How do we make it shine, because it's such a unique structure in this neighborhood and in Portland for that matter? How do we really uplift it? And we kind of went around and around on lots of stuff, and I think we ended up just saying, let's just plaster the rest of it. But instead of doing traditional plaster, we're doing an Efa system, and the term Efa a lot of times alludes to having a foam on the outside. That's not what we're doing. The Efa actually just means that the system is not, I'm not even actually sure, but what we're doing is we're putting up furring strips on the outside here, and to create a rain screen. We're going to put cementitious panels up, and then we're going to put a layer of a skim coat of plaster over that. So it will look very similar to old plaster. And then we design these little metal channels in here to give it nice, more horizontal lines. So now, which you can see in the final rendering, that has these sort of horizontal lines that will sort of really accentuate the Art Deco-ness, and sort of makes it now that we've made it a little taller, how do we sort of put some lines in that to sort of bring it down a little bit? So that's that. You can see the roof insulation that we were talking about. You can see that service cavity, my air barrier running here, taped and glued to this block here, and then the Aero barrier comes in and does the rest. That spray insulation that we talked, or that spray product that we talked about earlier. And then the vapor barrier will be the paint. And so the air barrier is out here. The vapor barrier will keep moisture from getting in there, but it's really not necessary because we've done this. Air barrier will also act as a vapor barrier. And so we don't even really need this, but it's sort of belt and suspenders in that case. We kept the something else I mentioned. We kept these kind of really unique overhang awnings because this is south facing and it's going to get hit with a lot of sun. So this will help us on our shading. We didn't do anything here because we just like kind of that look of that Art Deco. This door that was here is changing to a window too, so you'll see that. Again, around the back, you'll see this PT framing that we salvaged from the deck that was there. It was still in pretty good shape. We used these blocks were there too. We just reused them. We designed it so it would work with the stuff that was there. So we have 2x6s running this way. Basically, we just had short spans, and then we put our decking over that. And we reused the concrete that was there. Instead of doing footing, we just sit on top of the slab there. And then there's the juniper on the deck below and the juniper on the wall. And I left the juniper gapped, so you can actually see through the siding and actually see a lot of people, what they'll do is they'll put like a black screen so that these lines are just black and you can't see what's going on. But I wanted to be able to show people the rock wool underneath there, or the mineral wool, so you can actually look in these little gaps and see the mineral wool, which you're seeing here. You can see that gap right, you can see it behind there. And so the idea there is that this is just sort of like, this isn't doing much but keeping like heavy rain, heavy objects from damaging the wall, but air is able to just move through there, at will. Finishes on the inside, which this, thing is not, we're still working on this. It's a slow burn. It's hard to run an office and do your own build out. So, which I just learned. So the inside now, we've got the interior doors in, the roof is insulated. This is a little bit old of a picture, but the tile is starting in the bathroom. That's one nice thing. And so we did this really kind of interesting tile pattern in there. In the conference room, we're going to do this moss wall, which is preserved moss, and you sort of just glue it up to the wall and you create a pattern. It's really going to be pretty cool. Cabinets in the kitchen are being built, all FSC, exposing that Gutex for marker board, like I'd mentioned earlier. And then the wallboard alternative, instead of using sheetrock, gypsum board, which has a really high carbon intensity, and a lot of that has to do with the amount of heat that goes into drying the gypsum and the amount of and there's a ton of water that goes into that process. And there's also toxins in there. Some people have real high sensitivities. There are some toxins in the gypsum itself, which is, a lot of people don't know that. So there's a material out there called Magnesium Oxide, and it acts a lot like gypsum board. It doesn't take nearly the water amounts. It doesn't take all that heat to cure it. It actually, the chemical reaction of when it's setting up, actually absorbs carbon in its drying process. So while it's curing, it's actually absorbing carbon. So it actually is carbon negative. It is a newer product that's been around. It's been around for a while. Companies have been struggling to get it off the ground because it's more expensive, and I think there isn't a huge driver where people are like, we need to find an alternative for sheetrock, because there are all these other things that we need to find alternatives for. But this is important because I think gypsum is pretty intensive, resource intensive, and energy intensive. So again, as I had mentioned earlier, it's not much more expensive. Like a lot of these alternative materials, I think it's $4 more per sheet than a normal sheet of sheetrock at Home Depot, but it costs a ton to ship it to me. So it was $1,500 for the order, but it's another $600 to ship 2 pallets. So, that's a pretty big hit. So obviously you'd save some of that in a volume order, but they just don't have distribution. Where you'll see this product really starting to pop up is in the commercial world, as it is being used as floor layment for soundproofing and fireproofing. So it's super fire retardant, like way more than gypsum board. Alternatively, I will mention that if you do want to lower your impact for gypsum board and you don't want to deal with this magnesium oxide, you can have contractors put up lightweight concrete. So, or sorry, lightweight gypsum. So lip gypsum comes in more of a dense. The typical assembly of it is dense, and then they make a lightweight gypsum, which I don't think costs anymore, but it uses less water and less gypsum. It's lighter, it's easier to manage, so there's savings in the shipping of it because it's lighter. That's also true about the magnesium oxide board. It's super light, and so you save in that, and you save in the resources. So at a minimum, you should be using lightweight gypsum if you can, because it's just saving a ton of carbon. Finishes, wood, we've got FSC madrone going in this space. This picture isn't exactly accurate, but that will be in the kitchen area and the main area, a porcelain tile in the floor of the bathroom, and we're also reusing lath on the ceiling and the wall. That's another spot we're using the lath. And then that moss wall will be here. Our Gutex wall will be here. This will be all tack up board using Homosote, which is just like a paper product that is packed into a panel. And then we're using a couple of different commercial carpets that have backing that in the interface version of it, which is the Sequest backing, is carbon neutral. So I think the way that they achieve that is they're doing all this carbon negative stuff over here, and they really reduce the intensity and the nasty stuff that's in the carpet backing over here, and then sort of there's some offsets there. I don't think it's the product itself is neutral. And then the same with Shaw, has a very similar, it's not as good as the interface, but they also have an eco back that is fairly good. Here's some of the lath we're using. This is a picture of that magnesium oxide board. It looks a lot like sheetrock, honestly. And then inside, we're also doing some cool stuff on the ceiling. So inside this area where we had saved, gone to great lengths of saving this and trying to work around that, the plaster cove, we're inside the center of this. We're going to put this really cool mural of a wallpaper mural of a mountain scene. So sort of that pops up in a couple different places. The mini split out back, this is something that I think is interesting. So when you have a HVAC person come and, hey, I want to get rid of my gas furnace or whatever you're doing, and I want to do a mini split, or I want to do a heat pump system that ties into my forced air system, whatever your plan is. But if you're going to go to the system, what will happen is almost always the HVAC person will oversize the unit. They'll say, hey, I think it's going to be about this, but let's go with the bigger one. Or if we're on the edge, or they'll just say, yeah, I think it's this. It's 18,000 BTUs. Let's just put that in there. And it doesn't use any more energy because it ramps down. So it's got a variable fan, so it will slow down when it doesn't need to be full blast, right? So I thought, okay, well that seems right. But then I started thinking about the one thing that is not great about heat pumps is that they're filled with a refrigerant that is huge. It's like 10 times the global warming impact of carbon, right? That refrigerant, and it's not if it leaks, it's when it leaks. The stuff has a tendency to leak. And then once it does that, it's really, really bad for the world. Like, it's terrible. So I started thinking about, well, let's not oversize this, because when you look at down here, this unit is 9,000 BTUs. This unit is 12,000 BTUs, 15, 18. There's more refrigerant in the system, right? So now there's more stuff that can evaporate and get out there. So they were telling me 18, and I got them down to 12. I'm wondering if I could get down to 9, because you can see how much less refrigerant is in that system. Another thing that impacts this is where the unit is located. If the unit is really far away from the cassette that is blowing the heat, That's a huge line that has to get there. There's a little bit of loss in that line, so that's less efficient, but also that just means there's that much more refrigerant in the system because it's got to be filled all the way. So that's something else to consider when you're locating these. This is located right outside, straight line to the cassette. So we minimize that as much as possible. But also, this is just something I think people will oversize it because they don't think it runs more energy, which I'm not sure if that's true or not. But if I trust they're saying that, this is something they don't think about is the amount of refrigerant that's in it. And as an aside, the technologies are coming on for CO2 to be the refrigerant in systems. Sanborn, I think it's called Sanborn, has a system that's CO2. It's just really, really expensive. So you'll probably start to see that more often as the price comes down. We installed an ERV, and we installed it over the bathroom. So you can see it up here in the ceiling. It's just packed tight to the service cavity, underneath the service cavity. And the way, the ERV basically will bring in fresh air and will create a balanced system. So you don't get, when we pressurize the structure and sealed up everything with the Aero barrier, that type of condition doesn't usually exist, that you have this high pressure. And so one of the things, like if you have in your house, if you have a bath fan or you have a kitchen fan, when you turn that fan on, it creates a negative pressure in your home because there's no makeup air for that, right? So in a typical home, right? So that starts to pull air into that vent. And where does that air come from? Well, if your windows and doors are shut in the wintertime, all your fresh air makeup is coming under your door cracks, through holes in your walls, through your moldy bits and dirty bits. That's how your fresh air is coming into your home at that point, and it's pulling it in. So what an ERV does is it does a number of things. One thing is it gets rid of that negative pressure because it allows air to come in and out without, at will, and or when you have it turned on. So when you have it turned on, it brings in fresh air from the outside. It exchanges the stale air from the inside. So you constantly have fresh air coming in, and then there's an exchanger in there that exchanges the heat. So this unit is, I believe it's 90% efficient. So you're losing 10% of your heat as it's bringing in the fresh air. And then it also creates, again, that balanced system. So when the fan comes on to pull stale air out of the bathroom, it doesn't create that negative pressure and pull air in through the cracks, which hopefully we don't have any, but you know what I'm getting at. So we set this up so that it would pull air from the bathroom. So that's where the makeup air comes from. It pulls from the bathroom, and then it supplies to the conference room and to the workroom. So what that does is it allows us to then use this as a fart fan too, right? So someone goes, it can pull at a low pace, like just at a low fan speed, constantly, or at 20 minutes an hour, or however we set that up. And then when someone goes in and turns the fan on, the timer on, it boosts this to the highest fan speed, and it pulls all that air out of there, all of that bad air out of there, and supplies fresh air in. And then when the timer goes off, it goes back down to the lower speed, or goes off, however that is set up. We chose this Panasonic unit because of the efficiency, but also because it's one of the units that's the most compact, and this is actually installed on its side. They're designed to be sideways or upside down. The Brown units, which are more efficient than this unit, they're more popular. The Brown units, I think they're owned by what is the name of that company? The big company out of Germany. Either way, those units they have to be installed straight up and down because there's condensation that will drip out and the filters will fall out, all that kind of stuff. So they're not designed to be rotated. This one was designed to be in a tight space like this, so that's why we chose it. And it has a filter on there that you can upgrade to a better filter. So that's another thing with this Panasonic unit, is all the performance numbers are based on a MERV 8 filter, which isn't super awesome. They have a MERV 13 upgrade, but they don't have performance numbers on that. So the better your filter, the worse your performance typically, right? Because there's more resistance in the system. So this will be hidden up in the ceiling. There'll be a panel here that you can take out to sort of service this or change the settings. But that'll all be hidden up inside there. We had a solar analysis done to see if we could go net zero. they don't believe we can, but I don't know if I trust their numbers, because their baselines are based on, a normal office building built to code, not built like we've built it. So this would be, they did a rough layout. They tell you how much you can generate, so you can have this done for free. Energy Trust will actually, if you want to go down this road of going solar ready, Energy Trust will pay for a big chunk of this work to have this done. So they'll pay you $500 to just have this done, which a lot of these solar companies will do this for free. So that's something that could be pretty nice. So they sort of did this whole analysis, and they're saying you can cover 58. They're telling me that I can only cover 50% of my solar needs. So maybe it's not worth it. Maybe it is. It's sort of a cost analysis. Like, we will do it eventually. We don't have the budget right now, but we're going to set it up so that we can do it later. And then this is just sort of a breakdown on what you'll save and when the payoff sort of comes back. But for us, it's more about doing the right thing. Something else I would say about solar systems that I learned years ago, there's options to lease and there's options to buy. And, I never really, lease is usually like very cheap, right? Because they basically build it for you and you kind of pay a little bit, so you don't have to pay a bunch of upfront system. But when you buy it, it costs a little bit more, maybe a lot more, I don't know, but you have to pay some more upfront. But what I found is that when you lease those units, the company that installs it takes the credits, those renewable energy credits, and they sell them to the utilities. So now the utilities have said, okay, yeah, we're required to have X amount of kilowatt hours coming from renewables, and we're buying all this rooftop units, renewable credits, and we're using that. So instead of them going out and making more facilities and getting more systems online themselves, they're using your rooftop unit. And so you're not making the world a ton better, because you're just meeting the minimums of the federal government or whatever their internal goals are. So, or the state goals. So that's something to keep in mind between buying and leasing. If you buy it, you're actually above and beyond the minimums that are required for energy production. And then not a lot to talk about here is the site plan. We're going to replace this concrete here so that we can get the ramp up, and then we went to wood. So we're trying to limit, instead of doing concrete the whole way, trying to reduce the amount of carbon, because concrete is so carbon intensive. In fact, concrete accounts for 8% of the world's carbon. That's sort of, a lot of people don't know that. I think more and more people are learning that. It's the most carbon intensive construction material. So we tried to minimize that as much as possible. We removed concrete. The whole site was basically paved over with concrete. So we're removing it in the front to do some more landscaping, have more, less runoff, and reusing it where someone would probably re-pour this because it's not in great shape. But this says wood deck, but it's actually going to be a patio, the concrete. And so we're just going to grind it down and try to give it some new life, even though, it's not going to be in great shape. But we're just going to kind of live with that, remove it in the back so that the runoff from the roof will have a rain garden. And then when we bought the building, there was a 20-foot shipping container sitting in the back. I don't know if you saw that in some of the photos. So we decided that we'll push it in the corner, and we're going to put our bicycle storage in there, and we're going to reuse this thing, and sort of, why not, and then don't tell the city this, but we might have some meetings in there. So we pushed it up against the corner, and we're going to try to reuse that instead of just taking it off. And the door was already there, so it's all ready to go. So that is it.